In this second part of the session, I'm gonna be talking about pre-trained models and fine-tuning. So this is something quite common right now in the state of the art. Like many people uses pre-trained network on ImageNet, like AlexNet or VG16, VG19, and so on. And then based on them, or on those pre-trained features, they just take their own data for their own problem, binary problems or multi-classification or whatever, and just fine-tune the net. That means that the network is going to change, the weights of the networks are going to change a little bit, probably just for the classifiers and fully connected layers, and the rest of the network is going to be pretty much the same. So the initial filters, like computing features, basic features like, for example, edges or blobs or whatever, are going to be pretty much the same, while the last layers are going to be specialized in our new problem. So in this case, cats and not cats. Yeah, in order to perform these experiments, I have provided you with AlexNet pre-trained on ImageNet. So the first thing to do here is to load AlexNet pre-trained on ImageNet. Good. So as you can see, it's following a standard MatConvNet structure for the network, for the GAGNN network. So we have the parameters, the definition of the layers, meta information, in this case coming from ImageNet, with all the classes and so on. But anyway, so that's the pre-trained network we're going to use for our experiments. Right. Before I was using for the previous experiments like AlexNet trained B-norm binary, which was a modified version of AlexNet including batch normalization. For these experiments, I'm going to be using a more standard AlexNet version without the batch normalization layers, just because since we are going to be using weights coming from a pre-trained version of AlexNet which doesn't use batch normalization, things might get quite messy if we add batch normalization to the network while preloading weights from a network that doesn't use batch normalization. So in order to avoid this mess, I'm gonna be using this definition of the network, more standard without batch normalization. Okay. So yeah, this is the standard AlexNet we have been using during the last session. As before, the only change is to convert the classifier into a binary classifier. Okay, we have added these lines here just to select between doing fine tuning or standard Xavier's normalization when you don't have any pre-trained network or no pre-trained network is provided by the user. Okay. For these experiments, we're going to assume that all the data is in memory, so it's going to be fine. Yeah, it's gonna use this as a sort of baseline to compare with the later experiment we're gonna run with the with the preloaded pre-trained version of AlexNet. Sorry. So far so good. I'm gonna leave it for a couple of epochs just to compare later with what happens when you use pre-trained networks. Of course, in this type dataset, you are not gonna appreciate a huge change, okay? But for other cases, the difference is pretty dramatical. So using pre-initialization helps a lot. I always do it. I always use ImageNet networks, like I don't know, BG16, in order to initialize all my networks. It doesn't matter if if I'm doing classification or object recognition or semantic segmentation or whatever. I always use some sort of pre-initialization coming from ImageNet or from another large data set, like for example MIT places or so. Okay, we're gonna be stopping this in epoch 5. Okay, the plot for later. Okay, this is our baseline, our main reference, using just an AlexNet network trained from scratch. And now we're gonna see what happened when instead of that we use a pre-trained version of AlexNet and we just perform fine-tuning. See how I'm also passing the pre-trained network. Okay, as I showed you before, here I added some lines of code. If the script says that you are passing through a pre-trained network, then the initialization changed to initnet fine-tuning. Otherwise, we use a standard Xavier's initialization. Let's first gonna have a look to what's happened in initnet fine-tuning. So, okay, there are several things we need to take into account to do this new initialization. Initialization is quite easy, but in this case gets a bit more tricky for several reasons. Okay. The first we do is to call the initparams method of MatConvNet. This is basically allocating memory for the different parameters, okay, and calling the default initialization of each of the layers if they have one default initialization. But in any case, usually people want to perform their own initialization. So yeah, this is what we are gonna be doing right here. Okay, here on this loop, we're gonna be copying the parameters from the pre-trained network to our blank network. Okay, but I'm skipping some of the layers. Why is that? Okay, I'm skipping 8 layers, so until here, and that's basically because I want my new fully connected layers to be specialized on my problem along with my classifier. Okay, so I'm gonna be copying the structure of the network until here and reusing the weights coming from ImageNet, but for the fully connected layers I'm gonna be using my own. Okay, some people like also to pre-initialize the fully connected layers to what they got in ImageNet. You can do it if you want, but for this initial experiment we are not gonna do that. So if later on you want to play with this, feel free. Okay, so the second important thing to notice is that we are setting the learning rate very low. Why is this? Well, basically, like the majority of the network has already been trained for a really huge dataset called ImageNet, okay, for thousands of classes, and we can assume that it's sort of working fine. So in the initial filters, the representation achieved by the initial filters is gonna be sort of okay already. So we don't really need to optimize those weights that much. So those layers are gonna be kept almost fixed during the whole training process. That's why we are setting this learning rates quite low. Then for the remaining layers, like from the fully connected to the classifier, we perform the standard Xavier's initialization and set the learning rates to the standard values we use, in this case 1. So those layers are gonna be changing them drastically during the training process, while the remaining part of the network is gonna be using the pre-initialization from ImageNet, and it's not gonna change that much. So okay, this is pretty much everything you need to consider when performing fine-tuning. There are several strategies or several techniques to do the fine-tuning. So Benjus, for example, is recommending to start from the end of the network, like fixing all the network except for the last layer, adjust the last layer, and then keep adjusting the previous layers and the previous layer and so on in a sort of hierarchical way. That's a way of doing this. This is sort of the most basic recipe to do fine-tuning. Of course, you can choose many others. This is a nice research topic, and it's quite important to gain experience on this in order to solve your own problems using fine-tuning. So okay, let's gonna see now how this works in practice. Let's use the previous figure as a reference. As I said, you can expect to see a dramatical change in this case because the dataset that we're using is quite small. The classes are sort of simple, but in a general configuration, this step can change many things. So training from scratch is gonna take you weeks. Starting from a pre-trained model is gonna save you like thousands of hours. But still, here you can see how the network is starting from a lower error, like 56%, while before from 55. We already reached the objective point of 0.62. Okay. So we can see how the network has started from a more suitable point, which is the objective of this pre-initialization using ImageNet. Right now, we are just basically trying to find the parameters for the classifier and for the fully connected networks, which is a simple task. It's much simpler. Okay, this is gonna be the comparison after 5 epochs. Of course, it's not very fair to compare two networks after just 5 epochs, but just to have a general idea, well, we see that starting from a better point, so the objective was already 0.7 and moving down to 0.56, while the other network just moving down to a bit less than 0.7 in 5 epochs, and we reached like 26 26% of error in validation, while here in the previous case we're reaching only 0.34% of error in validation. So I hope this simple example is enough to convince you that doing fine-tuning is something useful and allows you to reach the result you want, like quickly and in a simpler way. So especially in those cases where you don't have enough images to do a proper training, so fine-tuning is the only option you have. You start training your network in a large dataset for a sort of as a sort of general recognition system, okay, that will be using ImageNet, and then you specialize it in your own problem using as many images you have. That's it. This is the second concept I wanted to explain you in this session. I hope you enjoy it. You sort of practice it by your own. So have fun.